Okay, Assalamualaikum and hello. So in the previous class I missed one of the slide, which is example 1. Okay, so let's do some practice here. So for A, synchronized speed and motor speed. So N synchronized is equals to, okay, recall back 120 and F divided by 4. So you know from here it is 60 Hertz and 4 volt. 120, okay, 120, frequency is 60, okay, divided by 4. So you get 1800 RPM. So that is the synchronized speed. How about the motor speed Nm? Okay, so the motor speed is actually, okay, 1 minus S and S. So this one from, okay, this one, okay, so okay, use this formula. I don't have the, okay, but it's basically almost the same. Okay, so 1 minus 0 0.05, okay, 1800. So for this one is 1710 RPM. Okay, so it's the frequency of the rotating in the rotating air gap field. So speed of the rotating air gap field is basically the same as synchronized speed, so it should be the same. So equals to Ns equals to 1800. Okay, so frequency of the rotor circuit, so you can see here, where is it? Okay, so the induction, okay, the field will produced by the stator. So in the air gap, the field also the same. Okay, how about the frequency? Okay, so for this one, I think in the note it doesn't mention. Let me check first. Okay, sorry, this topic is not too well organized actually, but it's okay. Okay, basically, okay, if your supply 50 hertz here, the frequency here is not 60 also. Okay, the frequency at the rotor and the stator, it will be different. Okay, so be careful. So how to calculate the frequency at the rotor? So frequency at the rotor is basically F, usually they call it F2, is equals to as F1. So F1 is the supply, this one is at the rotor. Okay, so F2 is equals to S is the 0.01 multiplied by the frequency is 60, and you get 3 Hertz. Okay, that is the frequency of the rotor circuit. Okay, this one inside the circuit, not the speed. Okay, we look at the circuit right now. Okay, so basically the frequency of the current at the circuit is different than the motor is different than from the stator. Okay, for this question, I'm not sure what is the meaning, so just let it be. Okay, and this one also I'm not sure what is the meaning of the question. So for E and F, just let it be. Okay. Okay, the topic is actually more towards imagination, so maybe I should add some animation to this. Okay, so I give you the first one.
Explain the principle of operation of a three-phase induction motor. We know that when a three-phase supply consisting of three phases and a neutral wire is connected to a three-phase induction motor, its rotor starts rotating. Let's understand what makes the rotor rotate. When a three-phase AC supply is connected to the three-phase stator field windings, They start behaving like electromagnets and produce three independent alternating magnetic fluxes. The resultant of these fluxes is called the net flux. We see that its magnitude remains constant, but position keeps on changing with time in circular manner. Hence, net flux develops a rotating magnetic field in the stator, which causes relative motion between the net flux and the rotor. Since the magnetic flux linked with the rotor keeps on changing, a current starts flowing in the rotor winding. As per the Faraday's law of electromagnetic induction, the direction of this current is given by the Fleming's right-hand rule. We know that when a current-carrying conductor is placed in a magnetic field, it experiences a force. Similarly, when a current-carrying rotor is placed in the stator magnetic field, it experiences a force and starts rotating. The direction of rotation of the rotor is the same as that of the rotating magnetic field of the stator. We can say that a three-phase induction motor works on the principle of electromagnetic induction, where the relative motion between the flux and the rotor caused by the rotating magnetic field induces a current in the rotor, forcing it to rotate in the same direction. Related terms are
Okay, so I also will show you another video. I have 3 videos here to show you, to make sure you understand how the induction machine works.
Whether synchronous or induction, three-phase electric machines use rotating magnetic field for its operation. To understand concept of rotating magnetic field for three-phase machines, consider this simplified winding. It has got just 3 coils. They are arranged 120 degrees apart. Magnetic field produced by a single wire carrying current will be as shown. For this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. Now have a close look at how magnetic field varies as current in coil varies. You can notice that orientation of magnetic field changes with current, but its magnitude remains the same. From these 3 positions, it's clear that it is like a magnetic field of uniform strength rotating. Speed of rotation of magnetic field is known as synchronous speed. The big question: how to quantify synchronous speed? This simplified winding has got just 2 poles. You can notice that magnetic flux is able to rotate through 2 poles when current take 1 complete revolution. So for 2-pole case, synchronous speed is same as frequency of AC current. Here is a case of winding with 4 poles. For the 4-pole system, magnetic field will again rotate through 2 poles for full revolution of current. So you can note that speed of magnetic field has become half this time. So for general P pole system, synchronous speed is given by this equation. In an actual motor, there can be 2 to 14 poles. This motor is having 10 poles. So for a 60 Hz power supply, magnetic field will rotate at this much angular velocity. Such a rotating magnetic field can make the rotor rotate for induction as well as synchronous motor.
Okay, I hope you can imagine how the rotational rotating magnetic field is look. Okay, another important thing that you need to know is the torque speed. Okay, torque, this is torque, this is speed characteristic of a induction machine. So you need to know the starting torque here, and then you have the breakover torque. Okay, So and then you have the speed, okay, the synchronized speed. Okay, as you go closer to the synchronized speed, the speed become more closer to the synchronized speed. Okay, when there is no load. Okay, but the torque is become 0. Okay, if you increase the load, so you can see here the slip increase. Okay, if it is near to the synchronized speed, okay, the slip is 0, but if you increase it, okay, torque is proportional to the slip in this region. Okay, you can see here you increase the slip. Okay, so I think this one is also important, so you need to know about this. Okay, now we continue with the equivalent circuit model. Okay, so you can see here for 3-phase wound rotor induction machine, you can see here this is stator winding. Okay, and you have an air gap here and you have rotor winding. So you can see here the rotor is short circuit. Okay, so in steady state produce magnetic field rotor of the synchronous speed. Okay, so in steady state, okay, the magnetic field rotates at a synchronous speed. That one I already explained. Resultant air gap field will induce the voltage for both stator and rotor winding. Okay, and the frequency in the stator is here, and slip frequency F2 in the rotor. So as I mentioned before, the frequency here is similar to the source, but the induced voltage here has the frequency is slip multiplied by the first frequency. Okay, this one. Okay, so make sure you know this, the characteristic of the equivalent circuit model. Okay, study and predict the performance. Okay, so stator winding per phase quality. Okay, so this is the equivalent circuit for the stator part. Okay, so you can see here stator part, you have V1, R1, X1 and RC, XM. So it is similar to the transformer, and this is E. Okay, E is the induced, where is it? Induced voltage. Okay, so it's almost like a transformer, but right now the magnetizing current, this one IM, is much more larger, 20 to 50% larger. Okay, if transformer is much more smaller, it's around 1 to 5% only. Okay, it's larger due to the air gap in the distribute winding. Okay, so because of the larger X1, the IM can become larger. So you have seen the stator part. Now we look at the rotor part. So when you look at the rotor part, is also almost the same. Okay, you have the X2 and R2, so E2. But you have to be careful here, there is a little bit different. You can see here there is slip. Okay, you can see slip here, right? So this parameter depending on the slip. Okay, so okay, this is the equation. This one should be at the beginning. Okay, but it's okay, you can use this formula. So basically the induced voltage here is much more smaller. Okay, so you can see here I2. Okay, this is just simple analysis. So ES E2 divided by R2 plus J S X2. Okay, make sure you include S. Yeah. So this is the power, of course. Power only look at the resistance. Okay, I squared R. Okay, now we look at this one. Okay, let me put it side by side first. Okay, you can see here V1 is equals to R1 I1 plus J. This one is X1. Okay, so this one X1 I1. Okay, J X1 I1. So this is just a Kichoff law. And E1. EAG is air gap voltage or back EMF, but just assume it is E1. Okay, this one is the constant. Okay, so this constant are usually given K and flux AG. Okay, okay. Next is the rotor part. So you can see here, if you look at the rotor, you can apply Kichoff voltage law here. Okay, so R2 I2 plus I to S x to J. Okay, this one is x2, right? W J W L. Okay, so this is just a Kichoff law. So E2 of course is equals to K F2 flux, okay, or SE1. So recall back this, okay. So it's something like this, okay. So for E1 is basically R2 divided by S I2 plus J 2 pi FL 1, okay. Okay, so we move on to the next part. So I2 is equals to E2 R2 divided by S plus J x2. So this one is just you divide everything by S. Okay, you get this one. Okay. So when you divide all by S, you can get this equation, and you can draw the circuit again. You can see something like this. Okay. So E2 x2 and R2 divided by S. So means that the resistance is depend on the S. Okay. So if you apply it to the power, okay, you can see here I2 squared R2. Okay, this one is something like this. Okay, the power I get. Okay, so from this circuit you can see here from this, okay, so if you expand this you can get something like this. So R2 plus this one, okay. So this is another model to represent this circuit. Okay, another thing that important is although the amplitude and phase are the same, the frequency is different. Remember that I said the frequency of this circuit, okay, the rotor, the motor circuit is different. Okay. Now we combine everything together, complete circuit, equivalent circuit. Okay. So for this case, we assume that the stator and the rotor has the same frequency. Okay, the turn ratio has to be taken into account. Okay, and the stator and rotor is equals to something like this. Okay, so E2 bar is equals to E1 equals to alpha E2. Okay, so I think I have to make it larger. So A is the turn ratio, of course, N1 divided by N2. Okay, so something like this. Okay, so almost the same as the what we call the transformer. Okay, except that you have this type of load. Okay, this one is the same, almost the same. Okay, okay, almost the same, but this one you have to change a little bit. This is the model. Okay, and this model is not convenient for performance analysis. So the power, of course, this one, as I mentioned before, okay, okay, R2 over S is also equals to this one, and you can see here this one is the power at 2, and this is for the mechanical power developed. Okay, so make sure you know power at the rotor side and power at the mechanical side. So P2 is equals to I squared 2 R2 or S P A G, okay, A gap. Okay, the power of the mechanical, you can see here, you just divide by S and 1 minus S. So you get something like this. Okay. Okay. So P is the power air gap. Okay. Something like this. You have to relate the P1 PA gap is equals to P2 plus P mechanical. Okay. So PA gap is 1. Okay. P2 is basically depending on the S, and P mechanical is 1 minus S. Okay. So make sure you know the relationship, because you will use this formula in your calculation. So let us look at the example 2. Okay, for example 2, okay, if you want to understand this, this one probably also not come out in your syllabus because this is calculation. But if you want to understand this, you can look at here. Okay, let me pause first. There is some sound from WhatsApp. Okay, wait. Okay, so I'm not sure whether I will show this or not, because this semester is quite simple actually, and if you want to learn about this, maybe you can look it yourself. Okay, this 15 is just multiplied by 746 is just a conversion from horsepower to watt. Okay, and then you have the mechanical energy is just a shaft power plus windage and loss. So this power just plus the loss here. Okay, you get the mechanical power, and then the synchronous speed, of course you have to calculate it. Okay, this one is simple. Okay, so you have to find the slip because they already give you this one. You can find the slip. So after that you can find the PG. Okay, PA gap, you recall where is it? This one. Okay, PA gap is just basically P mechanical is 1 minus S, so you get the PA gap. Okay, rotor copper loss, you just P2 is equals to, okay, slip multiplied by the power A gap. Where is it? Okay, this one. Okay, P2. Okay, rotor copper loss is just P2 we multiplied by. Okay, so it's just a simple question, but maybe this one is will not come out. Actually, most probably you have to focus on this only. Wait, okay, this one. Okay, humbly book. Okay, you have to look at 821, page 821. Okay, you have to make sure that you know this relationship: the P in, PS, P roto, PA gap, P develop, or P mechanical here. Okay, this one is the rotational loss. This is the output. Okay, something like this. Okay, this one is, I think, much more important. You need to understand how the power flow for the induction machine. Okay. Okay, I think some of the note is not complete, but I think this one can provide a better understanding. Okay, so this one you can see here. So RS plus J XS, this one you have already bring it to the primary part. Okay, so R, of course, R, and then this one is the mechanical power, of course. So you can see here the input is 3 Vs Is cos theta. So you have the power here, and then you have to remove the copper loss. Okay, so this one is the R1. Okay, this one use RS. Okay, basically you just remove this. Is this stator copper loss? Okay, and then you have the A gap power. Okay, power at the A gap. Okay, and then you have the rotor copper loss. You remove this one. Okay, this one is the rotor copper loss. This one is the stator copper loss. So you have P, okay, is equals to, so because this is 3 phase, you multiply by 3. If not 3 phase, you don't need to multiply by 3. Okay, so this one is the mechanical power. Okay, 1 minus S divided by S R I squared. Okay, so you have a rotational loss here, and then the out. So this is the relationship of the power loss, okay, in the induction machine or induction motor. Okay, this topic is actually only surface. Okay, so you can see here in the induction machine, okay, induction motor. Okay, so rotating magnetic field, I already show you how the induction motor works. It's also already show. Okay, equivalent circuit already show. Testing after this. Okay, the power flow diagram is I already show you how. Okay, so that's it. Okay, this topic is much more simple. Okay, this one I will tell you later. Okay, so if you can see here, example 7.1, this one is not come out. Okay, so this one will not come out. Okay, only focus on the sleep. This is a new syllabus. Okay, so only focus on the sleep. Okay, how to calculate the speed and everything. Okay, how to calculate the speed. Okay, synchronous speed, motor speed. Okay, and also you have to focus the power flow, how to calculate the power flow. Okay, so where the power go and so on and so forth. Okay, that's it only. So no need to focus too much on this one. Okay, you need to know how to draw this, how to calculate, not to calculate, how to label this. Okay, but you don't need to know how to calculate everything. Okay, this is just a simple one. But after this I will show you. Okay, so let me open the node here. Okay, so if you open the node, this one, induction machine. Okay, this one is actually an old node. That is a lot of it, but you need to know the no load test. Okay, and the roto test. Okay, you need to know what is the function, of course, what is the function of no load test and block roto test and how it is conducted. Okay, so if you want a more detail, I already include an extra note here, this one. Okay, induction motor test. So make sure you try to understand how to conduct it. Okay, no need for now, no need to calculate, do some calculation. Okay, but you need to know how to do it. Okay, why this method is conducted. Okay, for calculation, maybe I will show you a little bit how to do the calculation. It's basically almost the same as the transformer. Okay, so this one you need to know because in your next year, okay, next semester, you need to do this lab. Okay, this lab will be conducted. Okay, no load test, block rotor test, and equivalent circuit parameter. Okay, so make sure if you check back the past year question. Okay, let me show you past year question. Okay, so you can see there is a lot of question here. Okay, it is quite complicated. You need to know the input current and everything. This one will not come out. Okay, this one is complicated and you don't need to understand it. Okay, what else? I tried to find the past year. Okay, this one is very old, 2016 and everything. This one is a very old scheme or very old syllabus, so you need to look at a new one. Okay, the new one doesn't cover the calculation of the current and everything. Okay, so I hope you're clear. For this syllabus, it will be more easy. Okay. Okay, this is the last part of the induction machine. Okay, equivalent circuit parameter. So as you recall, there are a lot of parameter that you need to find here. See, there is a lot of parameter. So you have to do some experiment to determine the parameter. So no load test, block rotor test. Okay, DC resistance measurement. This is the 3 tests that you need to conduct to determine the parameter. So for no load test, you can determine the core losses and windage and frictional losses. Block rotor test, you determine the reactance, and DC resistance, of course, to determine the resistance in the stator. Okay, so the equivalent circuit test is used to predict the performance, okay, of the efficiency, power factor, current, starting torque, and the maximum pull-out torque. Okay, so first one is the no load test. So for no load test, the parameter of the circuit is RC. This one determine result of no load test. Okay, okay, this one is general. Okay, open no load test, like an open circuit test, give information about excitation current and rotational loss. Okay, so almost same like transformer, but transformer is open circuit test. But for this one, you have to find the excitation current and the rotational loss. Okay, this circuit is performed by applying balanced polyphase voltage 445 to the stator winding at the rated of 50. Okay, rotor is kept uncoupled from any mechanical load. It's basically there is no load connected to the test, to the shaft. Okay, so at no load, R1, X1, XM. Okay, so this one R2 is infinity. So, and then for the block rotor test, you can see here like a short circuit test on the transformer, almost the same, but give the information of the leakage inductance, leakage impedance. In this test, the rotor is blocked so that the motor cannot rotate, and a balance phase are applied to the stator terminal. Okay, increase the voltage until the stator current reach its rated value. So block rotor test, you basically just block the rotor. The rotor cannot move. Okay, and block rotor test should be performed under the same condition as the rotor current and frequency that will prevail in the normal operation. So when you want to test this, you just increase the voltage until achieve a stator current, achieve rated current. Okay, and IEEE recommend frequency 25% of the rated frequency of the block rotor test. However, for normal rotor is less than 20 horsepower rating, the effect of frequency can be neglected. Okay, so at full rotor test, you have R2 and is equals to 0, so you get the slip is equals to 1. Okay, so basically R2 is just 1. Okay, R2. Okay, you get the open circuit test. So equivalent circuit parameter, you can see here, no load block rotor test, you can obtain here the voltage, current and power. So when you do this test, you have to record the power. So for DC test, as I mentioned before, you find the R1 or stator current. Okay, this is example. You can do this example here. Okay, so you can find everything. Okay, this one, I think this calculation on it is out of our syllabus actually. Okay, but if this come out, I will tell you. Okay, but for now it is out of our syllabus, so no need to worry about the calculation, but you need to worry about the theory. Okay, if you want more detail, okay, let me pause the video first. Okay, so you can check back your e-learning. So I give you an induction motor test. So this note will show you how to do everything. Okay, this is the solution. Okay, how to calculate. Okay, so try to understand this. This is not compulsory for this topic, but you will use this in your lab. Okay, so try to understand how to calculate this. Okay, so that's it for this topic. Okay, I'm sorry about the notes because there is a change in the syllabus. It's actually being reduced. Okay, the original one you have to learn everything. Okay, but for the new one you don't need to focus too much on the calculation, mostly on the theory and maybe some calculation of power or calculation of speed. Okay, that's it. Thank you. Okay, you have finished up the syllabus. Okay, there is no more. Okay, I will maybe next week I will provide the what things that you need to do for the final exam. Okay, so but for now I still don't obtain what is the topic that will include in the final exam, so maybe later I will show you. Okay, that's it. Have a nice study week. Okay, good luck with your final exam. So thank you. Okay, and goodbye.